Let's start the new topic, mutual induction. In this, we will also see one event, and from his observation, we will start to analyze such kind of induction. So, it is very similar to the self-induction, but in the self-induction we were considered only single coil, but here we are putting two conducting coils close to each other. And when a steady current is passing through one coil, then the magnetic flux is linking with the another coil. So, in this process, if the current flowing through the coil, then an EMF is set up in the second coil. So the basic reason for having such kind of magnetic flux in another coil is and if you remember, this particular type of observation we have studied in Faraday's law. One experiment. And this phenomenon in which the magnetic flux is linking with the other coil is called mutual induction. So now consider a simple arrangement which has been given to us in this way. So here if you see that two coils are placed very close to each other, and in coil 1 a steady current is passing through this battery and the switch is open, that means current is passing through it. So here the I1 current is passing. And there is a rheostat for which the external current should be reduced. And now, due to the Faraday's law, there is induced EMF is considered or is produced in the coil number 2. And there is a magnetic flux, because when there is an existence of EMF, then there is a change in their magnetic flux. Now, how can you observe that there is the induction of EMF in coil number 2? So for that, here galvanometer is used to showing the deflection in their current, or we can say any type of magnetic effect. Now, for a given position of coil 1 and 2, they also follows the Biot-Savart's law, and here the flux in coil 2, that means phi 2 of coil 2 will be proportional to the current of I1, because it is as per the definition of mutual inductance. Therefore, phi 2 is proportional to the current in coil 1. Now, if I want to remove this proportion, then I have to put some proportionality constant, and here I am putting M21. Here M21 is the constant, but in general this is the mutual inductance appeared in coil 2 due to coil 1. So this is the actual understanding concept. Now, this is the correlation of magnetic flux. But if you remember that there is an induction of EMF also in coil number 2. So according to Faraday's law, the induced EMF in coil 2, the induced EMF in coil 2, I am giving it as epsilon 2. So it is minus d phi 2 because we only need the change in the flux of coil 2 with respect to time. Now, the value of phi 2 from equation 1 I can substitute over here as minus d by dt M21 I1. So that is equals to minus M21, that is constant with respect to time. So I am putting it outside of the differentiation, and di1 by dt is as it is. So this is my second important equation in order to analyze further mutual inductance. So here the M21 is known as mutual inductance of two coils. And this is defined as one system. Now suppose when I1 is equals to 1 in equation 1, I am writing over here M21 into I1, and now in this equation if I am considered that I1 is equals to 1 ampere, then the value of magnetic flux in coil number 2 is given by M21. So which kind of relation is coming out from this equation? So this is the most important statement because the magnetic flux is now directly related to the mutual inductance. In the self-inductance, the induced EMF was equal to the self-inductance term means L, and here the magnetic flux is equal to the mutual inductance, and therefore I can write down this mathematical expression in terms of a statement as the magnetic flux linked with one coil of a system of two coils for a unit current flowing through other coil is also known as mutual inductance of a system. Now, Suppose I am assuming that the current is in ampere and the flux is in Weber, then the unit of mutual inductance is given by Weber upon ampere, and this is also you can consider as Henry or capital H. See here again, whenever I am writing the unit in form of the name of scientist, then I am writing all the letters in small manner. And if you want to write a single letter, then you must have to write it as in capital manner. Now, here we have considered the current flowing as unity. But have you ever analyzed that what happens when the rate of change of current is unity? When the rate of change of current in any one coil, but here I am considered that the current is in coil 1. Per time, here unit time, is equals to di1 over dt is equals to 1, and therefore your equation number 2 becomes epsilon 2 is equals to minus m21. So here also the self-inductance and the mutual inductance are having the totally opposite sign with relation to negative, means induced EMF. So this is your equation number 4, I think. And this particular expression I can write in terms of a statement as the EMF generated in one of the two coils due to a unit rate of change of current in the other coil. Here we have considered the current in coil 1, and so the induced EMF in coil 2 is the mutual induction itself. Is called the mutual inductance of a system. Now, if we take di1 by dt as in ampere per second, and also epsilon 2 is in volt, capital V, then the unit of mutual induction becomes volt upon ampere per second, that is equal to volt into second into ampere inverse, that is equal to Henry, is equals to capital H. Now see, The dimensional formula here will be also similar as that of self-inductance. So I am writing here the dimensional formula for M is equal to M1 L2 T2 A minus 2. So this is the dimensional formula for mutual inductance. Now here we have flow the current in coil 1, but suppose the steady current flows in coil number 2. Then the EMF will be produced in coil number 1 and that is given by minus M12 into di2 by dt. Now you also consider in this equation also that the time rate of change of current in coil number 2 as unity, and therefore epsilon 1 is also equal to minus M12. And with this, the mutual inductance will be same in both the cases. Therefore, M12 is equals to M21 and that is equal to I am generally writing as M. And such result is called the reciprocity theorem. So with this, our theory portion is over in this particular chapter. Just one application is remaining. And so now we will solve the illustration as per your textbook.